recording, and we can begin this
Okay,
meeting.
got it.
All right then. Well, hello to all of our CSS members. Hopefully, you all are having a good week so far. Today we are joined by Metabob. If many of you all remember, Metabob actually came to one of our meetings last semester to talk about their Python debugging tool. And they're joining us again to talk about a AI based topic. So before that, I do want to mention some announcements. So CSSPI, our project initiative, Project Weekly in particular, is actually looking for an iOS developer. And the developer interest form is still open until the end of today. So if anyone knows Swift and would like to join the CSSPI project, many of its benefits include obtaining senior project credit, gaining project-like experience, and the chance to present to industry representatives. Then you all can fill that out. I will go ahead and post the link to the interest form here in the chat. So I just did that. Also, we have our bowling social coming up. We have it planned for next week, Thursday. So Thursday, March 24th, at 7 p.m. It's gonna be at Oak Tree Lanes in Diamond Bar. So if you all would like to, meet some CSS members, you all are welcome to join us for that. I will post the interest form for that as well. And yeah, that's pretty much our announcements. So without further ado, I'll hand it over to our speaker, Ben Reaves, to take the show. So go ahead.
Hi, my name is Ben Reaves, and if I'm looking off center, I apologize. Somehow all the notes got put on the monitor over there instead of the monitor here. So um, yeah, I'm from Los Angeles originally, so I'm familiar with Pomona, though I didn't go to Cal Poly Pomona. I certainly know a lot of people who did and who have done pretty well. So it's a good place. So I work at Metabob, which is a company that, as we say here, this is actually a little bit of an old blurb, but we basically make a system that helps identify bugs in code bases. And we don't actually, we're not Copilot, so we don't actually, automatically fix them. But what we do is we identify the problems, we identify the type of problems, and we generate an explanation to say what it looks like the problem is a security related bug or a other kind of bug. Okay. And I am going to be talking about one type of technology that we use inside, which is called topic modeling. So I'll go ahead with this and see if everything works. And if I freeze up or something, please tell me because I don't see the chat. Oh, there it is. Okay. So first of all, what is topic modeling? This is what we're going to be talking about today. What is it? What does it do? How the algorithm that we use, we're using something called LDA. If you're familiar with the LDA, that's what we're using. There are a couple of implementations of LDA, not a couple, there are a lot of implementations of LDA that we can use, and they all give kind of different results. So we have to kind of choose which implementation we use widely. And there are some problems with it. Nothing is perfect. If it were perfect, I wouldn't have a job, Okay, first of all, why do we want to do it? Okay. So here's an example. Spam filtering is a kind of a simple example that everybody knows about topic modeling. You train your model on spam emails and ham. You know what ham emails? You're all familiar with this. Ham is the emails that are good that you want, and the spam is the emails that you don't want, right? And one way to do it, one simple way to do it is you spot common words. If an email has a lot of red flags in it, like, free money, there's a lottery, your car warranty needs to be extended, then you can guess that maybe that's probably spam. But it's a little hard to identify ham email. So that's an example where you have one versus many. The topic model is probably going to come up with a lot of topics, and some of them are obviously spam, and some of them are good, and some of them you don't know. So you don't know what to do with those. But anyway, the output of this thing will be spam or nothing, right? Now, now, if you have more categories, you can do, for example, Gmail, they have better topic models now, so they can detect spam, whether it's social, whether it's promotions, and within spam, you can detect, different kinds of spam, phishing, just plain junk mail, stuff like that. Okay, so that's, a better topic model can detect multiple topics. And in our application, what are we trying to do? What we're trying to do is, given a GitHub commit message, we're trying to figure out what are you talking about. Are you talking about a security fix? That's pretty important. Are you talking about documentation? Then maybe that goes to a different department in your organization, right? If it's a bug fix, well, that goes to the software people. Okay, the algorithm people, right? So that is the kind of thing that we're actually doing, and the type of explanation that we generate is going to be different depending on whether it's a security problem, a documentation problem, or a bug, or some other thing. So the training we get is from commit messages and other messages that you get, that you send to Git. For example, when you commit something, you give it a little message. Now, some people don't give it a little message, and that makes things harder for us. But if you give it a message, here's an example of one that's obviously about documentation, right? So this is what we're doing. And I'm going to show you what's in the topic model. Here's typically what the topic model generates, okay? And this comes from some of our topic models. This is I think this is comes from our 75 topic model, and I'll only show you a few of them. So obviously the first one is something written programming. The second is about documentation or about unit testing. And the other one seems to be about legal stuff, documentation, legal stuff, something like that. And then, you can see them. And as you go down, it becomes a little bit less clear what they are, but still it makes sense. Like down at the bottom, number 33 is obviously about internationalization of the code, right? Number 38, not exactly sure what it is. Number 39, yeah, that's not great. And of course, they're out of order. That's another thing that is one of the problems. But this is the typical output of our topic model. Okay, so how are we doing it? We are actually there are several ways to do topic modeling. One is unigram. Okay, which is you look for words that are commonly appearing, like the first example I showed you. If you see the word free quite a lot, you can say it's probably in the spam category. If you see car warranty, it's also probably in the spam category, although you're not 100% sure. Maybe it really is legitimate. So that's one way. That's a really simple way. TF-IDF is a little bit better version of unigram. It's called term frequency, inverse document frequency, and you basically, for each term, that's a word, okay? You look at how often that a word appears in that document compared to how many documents have that word. So if a lot of documents have that word, and your document has that word, that doesn't tell you very much. But if your document has that word a lot, and most of the documents don't have that word. When I say document here, I'm talking, for example, if spam filtering, I'm talking about an email is a document. When I'm talking about our GitHub commit messages, actually that little commit message is a document. That tells you the important words in the document. And from that, you can figure out the topic. But the output of that just tells you, okay, I see these words, and this was really important in this document. And then by looking at that word, you can guess whether that's spam or not, or what it's about. That is commonly used. It's easy to understand, but we use something called LDA, which is better because this one uses multiple words. It uses co-occurring words. So for example, if you see documents about virus, okay, that could be about a computer virus. It could be about security stuff. It also could be about health related stuff. Maybe it's maybe somebody is saying due to the virus, I wasn't able to work today. It could also be a political thing. You know, somebody believes that the coronavirus was a hoax, for example. This presentation is from a couple years ago. So at that time, there were a lot of people believing that. And still now, you know, it's still a bit of a political issue. So it could possibly be about politics, right? So just the fact that you had the word virus doesn't necessarily medical. You need to know other words. For example, if you see the word virus and you see the word COVID and you see the word vaccine and you see the word I don't know, pandemic, then you're pretty sure what it's about. But if you see the word virus and you see the word vaccine, okay. But now you see, well, no, let's take a better example. You see the word virus and then you see hacker and then you see token and then you can say that's probably about security. So LDA is better because it looks at co-occurring words, the words that occur together in a document. There's also a method called NTM, Neural Topic Modeling. Amazon SageMaker uses that. Anytime you get involved with the neural network, as I think you all know, you need a lot more data. It's structured a little bit like an autoencoder that I showed to the right. It's really good for finding documents that are related to each other, but not necessarily what the document is talking about. And I don't know your background. Do you know what an autoencoder is? An autoencoder is something like describing to the right. It basically takes an input. In this case, I'm using an image, for example. Okay, you take a lot of input images, you reduce them down to, you see the pink. I don't know if you see my cursor on here. Do you see the cursor on the screen or not? Do you see? I'm
Yeah,
trying.
we
Okay,
see
good. Okay. So you see this little thing. It tries to reduce it to a small representation, and then it tries to regenerate the image. Okay. And it does this for a lot of images, and it tries its best to regenerate all of them. Of course, when you regenerate the images, you're always going to get some artifacts because you didn't encode all the information. So an example, Mona Lisa might get a mustache when she comes out. Anyway, that's one type of topic model. We don't use that because we don't have enough label data for a neural network. There's another method called sequence to sequence that's used for a lot of NLP, a lot of text processing, very powerful. You can get very high, and we have enough data to do that yet. We might now, we're looking into it, but that requires a whole lot of label data. And I don't think you can do much with unlabeled data. You can't really mix unlabeled and labeled data. That's one of the nice things about LDAs. You can also implement it in Keras or PyTorch or TensorFlow or various other kinds of things. So the implementation side is actually not that difficult. It takes a lot of CPU power, but you already know this. So there are these various, there's these various kinds of things, and we decide to use LDA because it can take partially labeled data. That is, it doesn't have to be all labeled. And as you can see, it kind of automatically clusters them. We don't have to tell it beforehand what the topics are. It will get the topics out, and then we can interpret those topics. So here's what the LDA is doing. Basically, what the LDA does is it assumes that a document is created by a number of topics. That's why it's called, LDA stands for latent directly allocation. Okay, latent means hidden. Okay, there is a topic in there, and when you look at a document like you're seeing here, you don't know what those topics are. You don't know them yet. The assumption is there are some hidden topics that is creating that document, and your job is to find out what those topics are. Okay, so it's described here. You first of all, you assume there's a number of topics. Then you choose a distribution over the topics. And then for each word, you choose a topic assignment. That is number 2. This is the training phase. So you choose a distribution, you assign a word to a topic, and then you try to generate the document by those topics that you assigned it to. Okay, so that's basically what you're doing. And there's a lot of variations in the ways you can do this. Okay, but that's the basic idea of LDA, is that there are these hidden topics from which all your documents are generated. Okay. And the trick is it was this Dr. Bly at Columbia University. I think he's still at Columbia now. And the trick here is, now you want, for each document, you want to allocate its word to not many topics, right? I mean, if each word is from a different topic, you can generate any that you want, right? Because, oh, each word is from a different topic. So there you go, I got my topics. So you want this, your constraints are to, in each document, you allocate its words to only a few topics as possible. But in each topic, you assign as few terms. When I say terms, I mean words. Okay, I'll explain the difference in a minute. You assign as few words as possible. So using these 2 constraints, what you end up with is topics which contain words that often occur together in a document, like virus and vaccine, coronavirus and COVID. They'll probably occur in the same document. Coronavirus and basketball probably won't occur in the same document, although they might, So what you're trying to do is you're trying to group the terms that occur together in documents. Okay. So there's some detail here. Yeah. Oops. Well, I'll go again. What you end up, what kind of distribution do you get? And I won't get into this too much because this gets really too complicated. Is you wind up getting 2 types of distributions that you deal with, and that you can choose any kind of distribution you want, but we use directly because they work best. Okay, so here's an example that you have the document topic matrix and you have the topic word matrix. Okay, so the document's topics matrix means it's a matrix of each document is on one line, or what topics did it have. So each yellow dot is a document, and one document might have had a lot of terms that are assigned to the sports topic, but it had some words on the science topic, some words in the politics topic. Okay. And you also have the topic to word, like for each word, what topic was it about? So, for example, the word referendum, that's green. That was very likely politics, right? The word planet. Okay, I should back up a minute. The topic words is for each topic, what words does it have? So the blue topic has words like planet and galaxy in it, but is unlikely to have the word referendum in it. And it's not too likely, but possible that it has the word ball in it. Okay, so that's the topics to words distribution. And I won't go into that in any more detail, but I think I got a repeat slide here. Sorry. This is the detail of how the algorithm work. I don't know. Again, I won't go into this too much because we use I'm not going to program this myself. If I program this myself, I'm going to make a whole lot of errors, and I'm going to spend months and months and months programming this and finding that I have errors. So what I really want to do is I want to find an implementation that's already used in Python, because that's where most of them are. And I also want to get one that has a rather large user community so that they hash out all the bugs. And there are 2. One is called GenSim and one is called Tomotopi. So which one should I use? Okay, GenSim. I like GenSim because it's very widely used. It's mature. You got a lot of researchers using it, a lot of groups from all over the world using it, and it's been very well debugged. It runs kind of slow, but maybe that's okay. The other one is called Tomotopi. It uses, I'll get into Gibbs sampling in a minute. Tomotopi is newer. It is a little bit more buggy, but when I say bug, it doesn't appear to have bugs in the algorithm. The bugs that it has are more like, you'll be training it for a day or so, and then the thing crashes in the middle. So we don't like that too much. But the result is better. We're getting better looking topic models. We get topic models that are coherent, right? Sometimes the output of the topic model, you look at all, those lists, that list of topics that I showed you earlier. Sometimes you look at the words there and they just don't make any sense. So that happened to us with GenSim. I don't know if it's because of the parameters I used or what, but they didn't look good. And Tomotopi just gave us better output. Now, why is that internally? I'm not exactly sure, but I think it's because they use something called Gibbs sampling. Now, if you're into the detailed statistics, I'll give you a little bit of a hint. So remember those distributions, those Dirichlet distributions I described to you, right? If your training data is long documents like Wikipedia pages, it's very common to test and train these on Wikipedia pages. That's how everybody kind of compares their models. In research papers, they usually do it on Wikipedia documents. If you have a long document, then you can make a really good estimate of exactly what that distribution is, right? But if your document is short, like a GitHub comment, it's harder to make an accurate estimate of what the exact distribution is. Let's say instead of a Dirichlet distribution, they were normal distributions, right? If you have a lot of sample points, I can tell you exactly what the mean and standard deviation are. But if I don't have many sample points, it's a little harder for me to tell you exactly where the mean and standard deviation are, okay? Now, we're not using normal distribution, we're using Dirichlet distribution. So there's a different way to find out what the parameters are of that distribution. One is called variational Bayes. That's what GenSim uses. The other way is called Gibbs, and that's what Tomotopi uses. Turns out Gibbs is a lot better for short documents. Okay, so we're using Gibbs, which is done by Tomotopi. I've tried to get GenSim to use Gibbs, and it just failed. So we're using Tomotopi. It trains faster, but it runs slower. That is an issue for us because, for any machine learning thing, there's training time to train your model, and then there's inference time, which is the run time. And we don't like that to be slow. But so Tomotopi is not perfect, but it's actually yielding a better topic model, so we're using it. And actually, in our system, we don't actually use, we don't run the topic model at the time that the customer is using our stuff. We're using that while we train another part of this system. Wait, it's a little messy. Now, how do you do this? How do you make a topic model using Tomotopi and using the preprocessing that I described? Here's an example, and this little 25-line file does it, okay? So I'll describe here. First of all, you have to tokenize your data. You can't feed the text directly in, right? Each word. Remember I talked about terms and words, right? Each word, your input document has words in it, and you got to split those words. Those are the tokens that you use in your training. Okay, so I'm describing here a really, really stupid, simple tokenizer, and I'll get into this because this gets important later. So you tokenize, which means you just split them into words, and then you make a corpus, which is a list of strings, right? It's a list of tokens. And then you train your model on it. There's various parameters you can use for training, but this is the line that actually trains the model. Now, you usually want to run through it in a loop for several times, different, multiple, and, you have to play with number of epochs and the batch size per epoch and all that. But this is one run. Okay. Set it up, you set it up, you train it, you set it up, you train it, you run it through a few times. Here you are doing the looping, the training, and now you can type your model summary out. And that's the list that I showed you earlier, which has the topic number and the words in the topic, number and the words in the topic. That's what you get out. And now it's time to run a test. So at line number 20, we're going to run the test. We're going to run it through the same tokenizer. We take a test file name, we read it, we tokenize it, and we have to do two things, actually. We have to try to, remember that colorful thing I showed you. It's trying to, it's going to take your document, and it's going to create, and it's going to try to create your document using the topics that it had trained, okay, above in line 16 or line 17. It's going to try to create your document. And then given that, what was your document's topic? And remember, your document is not only one topic. Your document probably has a combination of topics. In general, your document has a combination of topics. For example, if you had a document, let's say you're training on newspaper articles and your document had things like, because it was suspected that he had COVID, the Olympics, this Olympics competitor was not able to compete. Well, that's about sports and about medical, right? So each document can have, it is normal that a document has a combination of topics. Now, in our case, we want to know what the main topic is, but actually you get a topic distribution and a log likelihood score for each of those topics. And then you look out what the now for our application, we look at argmax, which is the topic number whose log likelihood score was highest, right? And then we just say what the winning topic number was. So that's just a real simple version of what we're doing. Okay. And it just works perfectly every time, right? No, it does not. And here's why. Look at our data. Our data source is GitHub. And you know what you do when you commit stuff. At first, you have a nice comment. You created the main loop and timing control. That's a great comment. And then you abbreviate your comment a little bit, and then you get a little bit lazy and, it's more code and kind of crap like this. And, this is reality. This is what we get. We got a lot of junk. Okay. So, yeah. So one of the things that we need to do is we need to weed out the junk, because remember I said very early, our ultimate goal is to create an explanation, right? Okay. Our explanations cannot have words like hands and ASDF. We can't have words like that in our explanation, right? And some of these things are no sense. In fact, one of the most common messages we see is thanks or LGTM, looks good to me. That's one of the most common things we get. And we can't have that in our explanation. Our explanation cannot say things like, hey, thanks. What? That doesn't help me fix my code at all, So we have to weed out those kind of things. So that's one of the problems we get. Excuse me. That's one of the problems we get. The other one is, when you, as I said earlier, when you train the model, you have to choose all these hyperparameters. How many documents per batch? How many epochs? How many times you want to run that batch through? The more you do it, the slower it runs, and you don't necessarily get a better topic model from it. You just have to play with these parameters. Also, I don't know if you remember those topic distributions. You remember some of the, I'll go back here. These distributions here. In some cases, all of these points are around the middle, okay? And in some cases, distribution of your input documents is very pointy. This is very pointy. Okay, a lot of science only ones, a lot of politics only ones, a lot of sports only. And you don't have many that have combinations of topics in them, right? Okay, but for some things, all your like a journal. If you're training on somebody's journals that they write at the end of the day, right? They'll have a lot of topics mixed in together. They might talk about the basketball, the game that they played earlier in the day. And in the same document, they're going to talk about some political issue, and they might talk about something they learned in their classes, right? So that's an example of one. Golly, would you? Sorry, that's my mouse is just too jumpy. For that one, you have a lot of distribution in the middle, okay? So I'm talking about this because depending, here it is, these alpha and beta parameters, you want to choose them depending on what kind of input data you have. If you have a lot of documents that have, each document has many topics in it, it's all mixed, like you're training on journals, then you want to have alpha very low. And that second distribution, if they're also all in the middle, you want beta to be very low. If they're very pointy, you want alpha to be high and beta to be high. And that's something this model, unfortunately, doesn't really learn. You have to tell it, okay? Also, another issue with LDA is word order is ignored. Like coronavirus is one word, but for example, the word pull request, right? Some people write the word pull request as two separate words, pull request, okay? Request pull is probably not the same as pull request. That's a bad example, but it doesn't look at the word order. It's just a bag. Each document is taken in as a bag of words, okay? So that's another, one might say it's a problem with LDA, okay? We also LDA doesn't look at things like bigram, like pull immediately followed by request is a noun. That is a pull request. That is one noun. If you separated them, the tokenizer will separate them and it will not treat them as one word. It'll treat them as two. So it's like a document that said the word pull and had the word request in it somewhere else, and that's different from pull requests being together, okay? It's not using bigrams. You can make it use bigrams, but it doesn't use bigrams out of the box. Bigrams and trigrams are like string of two words or a string of three words that often occur right together. The other problem with LDA, and this is with any of them, is, as you know, when you train a neural network, you always have a loss function. That's how you train it. That's the basics of how you train it. You have to have a loss function, and then you evaluate your model by what's the value of the loss function, right? A higher loss means a worse model. You feed it back and you modify your hyperparameters and all the weights based on that feedback. With LDA, how do you evaluate whether your topic model that you got out was good? I do it by looking at it with my eyes, but that's really not great for tuning the model because I want to try a bunch of different alphas and betas and Ks, right? How do I know what is the optimal one? Well, if I just have to look at each one myself, then training is going to be awfully slow because I have to look and just evaluate it. So there are methods. One method is by accuracy of prediction. Accuracy of prediction works really well if you're just extracting one topic. We're extracting 100 topics. So accuracy is not going to work. Coherence is the measure that we use. And that's actually something we're battling with right now. There's several different coherence measures. And basically the coherence measure is measuring how well you did those two. Remember, there were two constraints, right? I'll go back here for a minute, just a minute. Remember these two constraints, and each document allocate its words to a few topics, and each topic assign high probability to a few terms. The coherence is measuring how well you did number 1 and 2. How well was it done? Okay. Does each document have only a few topics? And in each topic, does it have only a few terms? And when you look at the terms and the topics, do they really occur together within many of the documents, or are they all over the place? That's what the coherence is trying to measure. And there are a whole bunch of different ways to measure the coherence, but at least it's automated, right? At least you can do that. So that's something we're actually dealing with right now, is what coherence scores should we use to say that we have the best set of hyperparameters? It's hard. It's not clear which coherence measure is better. There's various different kinds, and there's a lot of papers on which coherence measure correlates well with evaluations by eye. There are a lot of papers on this. And if you want to write a paper on it, that's a good thing to write about. Another thing is data cleanup, and I'm going to get into that if I have time, and it looks like I do have time, because any machine learning thing you do, any, not just topic modeling, but anything, is you're going to have to do data cleanup, okay? And tokenizing, I talked about a little bit earlier, and lemmatizing is part of data cleanup. For example, here in this example, this is very clean, created main loop and timing control, except you have this little ampersand. What do you do with that? That's not really an English word. Well, you got to filter that out because and is a really common word, and you'll find that it's over all the documents. So you have to pull that out. Okay. And the word, dang it, the word created, well, if they said, what if they said create main loop and timing control? That's basically the same information as created main loop and timing control, right? So the word create and the word created really should map to the same term, right? They shouldn't be separate, because then you need, you know, in order to train anything to recognize topics or speech or anything, you want to reduce the dimensionality. That's a kind of a general thing. You want to reduce the dimensionality, which means you don't want to have terms like created, tokens like created and create in your training set, because, you know, then you have to have more data to make a model. The word create and created should go into the same token, create. Now that's easy for words like created and enabled. How about misc? That you got to expand, not contract, to miscellaneous, right? Okay. And what if you have words like fought? I fought a bug today. I was fighting this bug today. Well, the word fought has to change to fight. So this lemmatizing actually becomes a little bit complex, and you really need to know a lot about the language that you are lemmatizing in. And we typically, in the past, people have used NLTK for that, and we're using something called SPACY3. And I'll show you a little bit more. I'm going to go as far as you let me go, but this data cleanup is something that a lot of startup companies, CEOs, when they start up a company, they kind of ignore. They just say, hey, we're going to hire a bunch of engineers. They're going to make a nice machine learning model for us. We got a lot of data. Great. And what happens is the engineers come in, they look at the data and they say, wow, this stuff needs to be cleaned up. It always needs to be cleaned up. And the effort cleaning up the data is overwhelming, gathering the data and cleaning it up. So here's the kind of stuff that we're dealing with in our particular example. Typical content, bump up to version 1.1, okay? The lousy tokenizer is going to do a really simple job. It's just going to split the words, bump version 2, 1.1. You can already tell what's the problem with this. 1.1, well, it could be 2.2, it could be 2.7. That really should go into a number, not a 1.1. It should be said, oh, it's a floating point number, right? Here's another one, the thumbs up. Our model really deals with only English, and we don't deal with emoji. So again, lousy tokenizer is just going to split these up. Okay. What happens if you run it through the lousy tokenizer and create a topic model? Here's the kind of stuff you're going to get in your topic model. Okay. Topic number 0 is image, input, set, memory, method. That sounds good. Now here's topic number 1. This is garbage. You got XML in here. HTML in here. You got pieces of HTML in here. You got backquotes in here. This is not going to work well. This is a lousy topic model. Okay. So this is an example. So at least what do we need to do to clean it up? One thing, remove stop words that are really common, like I is the, not a, thanks, things like that. Um, delete non-English, but keep jargon. This is actually very hard. So deleting non-English word is really easy. The Spacey 3 module does that for you very well. Okay. But there are some non-English words that we need to keep because we're dealing with Python code, NumPy, README, all these, TensorFlow, all these Python module names. We got to keep them. And some of them are English words, but many of them are not English words. Okay. So I'm going to try to go through this kind of quickly because I'm not, well, I guess I'm okay. So here's the kind of lemmatizing we do. We're using something called Spacey. These are the developers of Spacey. The lousy one would say, I'd agreed to do that. Okay, I'd agreed to do. Now, a better tokenizer is going to eliminate a stop word. Had is a stop word here. To is another stop word. Do might be a stop word, might be not, but it's an important verb, so keep it. Okay, I agreed to. Okay, that's a little tokenizing. Okay, now lemmatizing. The word fixed should go to fix. The word caught, that's what I was describing a moment ago. What you really need to do tokenizing and lemmatizing together, it's not like a sequential pipeline. Here's an example. I'd like to do something. I'd agreed to do that. Okay. Is that I had agreed to do that or I would agree to do that? Right? Now you actually need to know not just what I'(D) is a contraction of, but it kind of depends on the other words in the sentence. So my point here is that to do lemmatizing properly, it really requires a module that knows a lot about the language that you're actually lemmatizing. And in this case, it could be I have or I will. If the I'd is from I agree to do it, I think I had sounds funny. So it's probably I would agree to do. Okay. But if this were past tense, I'd agreed to do it, it's probably I had agreed to do it. Now, in this particular case, it doesn't matter because had and would be taken away by the tokenizer. Okay. So you can see how the lemmatizer and tokenizer really need to work together. Okay. And that's complicated. And I didn't want to rewrite that. And in NLTK, I've used NLTK a lot, and NLTK really doesn't help you a lot with that. You have to run your tokenizer and lemmatizer back and forth a few times, and it's messy. Spacey is nice. Okay. The other thing you need to do is entity recognition. In the previous example, 1.1 should have been a number, right? Apple could be a corporation or it could be a fruit. Depends on the context of the sentence. A really good entity recognizer in your front end is going to do a proper job of, okay, Microsoft, that's definitely a corporation. Apple could be either one. Maybe it depends on whether it's capitalized. Maybe it depends on the context. My Apple iPhone, that's definitely the corporation. I dropped the apple on the floor. That's probably the fruit, although you could have dropped your iPhone on the floor. Anyway, so you need to do those, and that will give you a better topic model. I use something called Spacey that was written by these Ines Montani and Matteo Hannibal, and it's really good. Now, when we use that front end, we get a much better thing. You can see bump version of 1.1. You see the word 2 was eliminated, and the word and 1.1 comes up to a version number here. Okay, and here you got rid of the thumbs up. You got rid of the stop words. Okay, and after this, you create the resulting topic model is actually a whole lot better. So that's kind of the end of what I wanted to talk about today. I hope it made sense. I think I ended kind of abruptly here, but if you want to explore further and you want to try to use these yourself, here's where it's from. The Tomotopia is actually from this guy's GitHub repository, and he's getting more and more users now. It runs fast. The main documentation, however, is in Korean, which I do not read, but he does have English documentation too. And he responds pretty well, this the developer. Um, the nice thing about Tomotopi is the API is very clean, and he also has a lot of modifications of LDA available, like labeled LDA, where all of your data is labeled, PLDA, partially labeled LDA, where some of your data is labeled. And there's something called a hierarchical LDA. And as far as I know, GenSim does not do this. If you want to use GenSim for these other types of LDA models, you're going to have to kind of redo it yourself. PLDA is really, really nice because you start off with LDA because you have no labeled data. And then you have your higher labelers, and then you get some labeled data. So the PLDA actually helps. It's giving you a better topic model because you have some labeled data. Okay. Spacey is the tokenizer and lemmatizer that I described a moment ago. And this is where you get that. It supports over 30, I think it's more like 30 or 40 languages now. They've gone to a lot. Their English support is good. Their German support is good. Other languages, And that's pretty much all I wanted to get to. I hope that this made sense to you all. And if you have questions, I would like to hear. And I don't hear anybody, which means, oh, you're all muted.
Yeah. But yeah, to all of our members, if you do have any questions, feel free to put it in the chat or to unmute yourselves. But yeah, this is a very interesting topic. I can see like some user or some scenarios where a lot of the topic modeling could be useful.
Oh yeah, a lot of language. So my background is speech recognition. So
Right.
I'm actually more familiar with. I was a double E major, not a computer science major. Okay,
Okay.
that. When I went to college, I went to USC.
Oh, okay.
So
Nice.
it's not really a rival of yours, but it's across town, downtown in that really safe area of downtown. And at that time, computer science is what you did if you couldn't understand the double E classes. I think it's the other way around now.
Hey,
Yeah, the CS people are getting the jobs at Google and Facebook and Apple, and the double E's are like, uh,
Dang.
what do? You going to make a motor for us or something like that? No, no. So, yeah. But I'm trying. I never was formally trained in CS, but that's what I'm doing. And my background is more like signal processing of speech, and speech to text works now.
Yes,
Why does
definitely.
speech to text work? It's because you can train a neural network, and the neural network, if you have enough data, can do a better job than the old style of, extracting the Mel frequency capsule coefficients and running it through a hidden Markov model, which has latent phoneme recognition. And, that was fun. And I know how to do all that. And it's really complex, but, the neural network, you
Yeah,
just
it
get a lot of
revolutionized
data,
things.
you label it all up. Huh?
Like the neural networks and
Yeah.
implementations that definitely like revolutionize, the speech recognition area.
Absolutely. So now what's going on with speech is speech to text works, but then interpreting. Okay. So somebody said, do I need an umbrella tomorrow? Well, are you talking about weather, or are you talking about fashion, or are you talking about something else? Insurance. There's umbrella insurance. Are you talking about insurance? So, for speech recognition, this topic modeling is actually becoming really, really important now. It's like,
Really?
so which database are we going to? Are we going to our weather database that knows about the weather in the next few days? Or are we going to our fashion database that says, but tomorrow you need a pink umbrella, not a green one, because you're going to be wearing your pink shoes, or something like that, right?
Yeah, definitely. So we actually have a
Yeah,
question for one of our members.
great.
They wanted to know about how did you get into like data science slash machine learning? Does it require additional education slash schooling?
Oh, good question. So how I got into it is, I'll tell you exactly how I got into it. It was with my speech stuff, and I was working at Central Research Laboratory in Panasonic, and I heard about these neural networks. Well, wait, let me go back. How did I get into machine learning? Yeah, it's because of speech recognition. I just got really interested in speech recognition. I was doing signal processing. I was double E student. I was like, well, what am I going to do after I graduate? I could work at one of the big aerospace. Well, you guys are in Southern California. You know how this is. The big employers are these aerospace companies, right? Like Hughes. Well, Hughes isn't as big as they were. I think you have, what do you have? Control Data, isn't that in Pomona?
Not sure,
Um,
but I know one of our biggest ones is JPL.
yeah. So JPL is a good example. So you go to JPL and you know what they do? They do a lot of image processing there, right?
Yeah, definitely.
And JPL is getting, so my father was an astronomy professor, so he dealt with JPL a bit,
Oh,
although
okay.
he didn't do image processing. But what's going on there is there's so much images coming back now, right? And they're compressed very highly, right? So they're compressed and they're decompressed, right? So one of the things you have to do is, if you see an artifact, is that an artifact caused by the decompression? Or is that an artifact that's really important? Like, the volcano on Io, right? On the moon Io.
I
At
believe
first,
so.
yeah, at first they thought that was an artifact because it's a perfect circle. It's like the moon is here, it's very bright, and there's this perfect circle. So the engineers in that lab said, it's such a perfect circle. I'm sure that that's an artifact. It's nothing interesting. Okay. But there was an astronomer in that group who said, Io is located at a certain place where it gets squished around a lot. So it makes sense that it has that. So turns out she was right. Although that doesn't answer why I found that fascinating. But basically, I was working in hardware for the first 2 years, hardware design, the first 2 years that after I graduated. And I just got tired of it because, hardware, it works one day and it doesn't work another day. And you just don't know why. It's
Yep.
FM, and I'm not going to describe what FM means. It's magic. It's like, why does this thing not work today? I got frustrated with it. So I thought, I like speech stuff. I like audio. I like music. I like audio. And what is the audio that gives you the most feeling, right? Well, music, but speech, you're communicating information. To me, that was fascinating. I wanted to do more stuff in speech, and I kind of like languages. So that's how I got into it. So, okay, well, we got to learn these weird models. Okay, well, it turns out that they're complicated. And a lot of people working on speech, they want to do speech therapy or something to improve people's speech. That's nice. I really wanted to recognize, what was in there, what's being said. How can I remotely control something without touching it, right? To me, that was fascinating. And that's how I got into it. It's like, okay, choose something that you're really interested in and then do what's needed to do it. And for speech, that was machine learning. And now machine learning is everywhere. And that wasn't even neural network at first. At first, it was something called DTW, dynamic time warping. And then when I was about 25, Bell Labs came out with this thing called hidden Markov models that worked really well. And yeah, and now it's all neural network. That's how I got into it. And when I was at Panasonic, yeah, that's when I first used neural network. And man, that thing required so many resources. It required more memory than any of our machines had, more disk space. So what I did is I learned how to use NFS, and I basically network mounted everybody else's disk. And they got kind of angry at me because, their disks were filling up and they weren't using it, right? I said, yeah, that's me.
Dang.
And I have to keep working on this because it takes a week to train. Sorry, everybody. I'm going to be using all your disks and all your CPUs for a week. Yeah, sorry. Sorry. This American guy comes in and uses all our stuff. What, That was in Japan, not here.
Oh, okay.
Yeah, yeah, they weren't happy about that too much. Yeah. Of course, I said, well, you only, I mean, like, which was true at that time. Well, I need 20 gigabytes for my data, so I need to commandeer like 10 of them. Sorry. Yeah.
Well, yeah. Well, that's an interesting story on how you initially
Well, the
studied.
thing that's nice about machine learning now is that you don't have to do all this stuff yourself. I
Yeah.
mean, programming all the adjustments of all the weights, that is such a pain. Now, you take Keras. I mean, Keras has got to be the easiest thing, right? It runs on top of TensorFlow.
Mhm.
And, the hard part now is getting your data source and cleaning it up. That's the hard part.
Yeah, definitely.
And that's not going away unless somebody magically finds a way.
Hmm. That might be the next breakthrough thing.
Believe so. I actually, where I live now is actually right between Apple and Google, so I kind of hear stuff. And yeah, absolutely, that is exactly what they're working on. They're working
Mhm.
on that is hot right now. How to do automatic cleanup,
Yep,
automatic data augmentation. Oh yeah, that's the hot topic.
for sure. That might be a nice research topic for anyone.
It already is. But
Yeah.
if you can get somewhere,
Hmm.
basically, if you can learn what it is and what are the useful tools, you got a job.
Definitely.
Oh yeah, yeah.
All right.
But you
Well,
don't want to implement any of these things from the ground up yourself. It's good to know how they work, but
yes,
you don't want to start, implementing your own tokenizer and lematizer and LDA modeler and neural network from scratch. Don't do that. There's already good ones available.
definitely.
Yeah.
Definitely. All right then. Well, I guess that will do it for this week's meeting. Yes, thank you very much, Ben, for joining us
Oh,
on this
sure.
workshop. And
Yeah.
thank you, Rika, for helping setting this up. Really do appreciate it. Hopefully, our members did as well with getting insight into the whole AI/ML world. Um, and yeah, so without further ado, we'll go ahead and end this meeting off. And to our members, we hope you have a good rest of your week. Bye, everyone.
Thank you. Bye.